start simplifying it, something cancels, and instead of a vertical asymptote, I get a hole. So let's see if that happens. Everybody's on page 9, letter G. Here we go. What do we do first? Factor. Okay, now the top, factoring the top is pretty easy. How does the top factor?
X minus 6, X plus 1.
Watch it now. What is it? You might think 3 and 2, but it's not 3 and 2. It's 6 and 1. We need 6 and 1 this time because of the signs. So we're going to have y minus 6, y. X minus 6 and x plus 1. All right, now what about the bottom?
You have to group.
You have to group it. This is what we talked about in the last chapter. There's too many numbers there. So we'll look at these two. What can I take out of those two? X squared. And I'll be left with x minus 4. Yeah. Now what can I take out of these two? Negative 1. And I'll be left with x minus 4. Remember, if you take out the negative, your x will be positive and your 4 will be negative. Right? It's like reverse distributive. Now notice these match, don't they? That is really good news. That means that you can factor out the match and then group together everything else. So these are the matching ones. I'm going to take them out and write them right here. And then that leaves me with x squared minus 1. Now what about x squared minus 1? It factors into what? How does this factor? X plus 1, x minus 1. And now we're all excited because we can cancel. And our new equation is this. Right? Now, the fact that you canceled means you're going to have a hole in your picture. And the hole is like a point. Its x coordinate comes from what you canceled. So look at what we canceled out. What will be the x for my hole? Negative 1. Remember, we always do the opposite. Now, how will I get the y?
Plug it back in.
Plug back negative 1, plug that back in, and where do I plug it in at? Right here, for the x's. Right here. This is my new problem. Okay? So here we go. Plug in negative 1. Let's see, I get negative 7 on the top, right? And then I get negative 5 times negative 2. All right, what does that end up being? I put in negative 1 for all these spots. Negative 7/10. These two will cancel, but you still have a negative. 5 times 2 is 10. So, there's a grid there. I'm supposed to be graphing this. So I'm going to have a hole at the point negative 1, negative 7/10. I have an open circle.
I know where 7/10
It's between 0 and 1. It's less than 1, right? It's less than 1. So it's between 0 and 1. Now, you could also change it to a decimal and think it was 0.7, if that helps. Now, are there any vertical asymptotes to this problem? There are. In fact, there are 2 of them, because we still have 2 parentheses in our denominator. So we're going to have a vertical asymptote at 4 and one at 1. So at x equals 1, 2, 3, x equals 4, I have vertical asymptotes. Vertical asymptotes come wherever the denominator is 0. The denominator can't be 0. So whatever x cannot be is going to be a vertical asymptote. Now, here's the tricky one. Oh wait, we're not ready for, we haven't done horizontals yet, have we? This is it, we're done. Vertical asymptotes, got it. Now, I was getting ahead of myself. Look at the next section. It says find the horizontal and vertical asymptotes. Now, vertical is easy, we've already done that. But horizontal asymptotes, there are 3 things I want you to pay attention to. If you pay attention to this, you'll get your horizontals easily. All right? When you look at a problem, and they're all going to be these kind of fraction type problems. So when you look at them, there are really 3 things that can happen. You can have a situation where you have some x's. You don't have to write these down, just look for a minute, and then we'll write down what we need to. I'm just giving you some examples. Or you have some squares over some squares. You can have this kind of problem where you've got the same power on the top as you have on the bottom. Then you can have the kind of problem where you have maybe some x's over some x squares, or some x squareds over some x to the 5th. In other words, you can have a problem where the power on the bottom is bigger. Okay, so the powers can match. The power on the bottom could be bigger, or, what's the other thing that could happen? Power on top could be bigger. So you might have something like 3x squared minus 8x plus 2 over 5x plus 1. Or 7x to the 5th plus 8x squared minus 10 over 3x to the 4th plus 2. Something like that. Your horizontal asymptote, wherever it is, depends on the relationship between those powers. If the power on the bottom is bigger, I don't care what else is going on in the problem, it doesn't matter. If the power on the bottom is bigger, your horizontal asymptote will be y equals 0. Okay, you need to write that down. If the power on the bottom is bigger, I call that bottom heavy. If the fraction is bottom heavy, if the power on the bottom is bigger, then your asymptote will always be y equals 0. I'm talking horizontal now. Horizontal asymptote will always be y equals 0. So there's no work for you to do. Your little eyeballs zero in on the problem. If the power on the bottom is bigger, it's y equals 0. If the power on top is bigger, there is no horizontal asymptote. So you would write none. If you had to give a horizontal asymptote for one of these problems, you would say none. So write it down. If the power on top is bigger, there's no horizontal asymptote. Okay, so 2 big rules so far. Power on top bigger, no asymptote. Power on bottom bigger, y equals 0. Now, what happens when they match? Well, then it's really easy. If they match, you just look at their coefficients. So this one would be y equals 3/4. What would this one be? Y equals 5/6. That's all there is to it. Finding horizontal asymptotes is a cinch.
What if there's
There
an
are
X?
3, it won't be. It'll always be y equals.
No, what if there's an X? It's just an X on the bottom.
Well, if you had a squared on the top and just an x on the bottom, it would be an example of this. The power on the top is bigger. Remember, you're comparing those powers. If the one on top is bigger, no asymptote.
I think he means without a number. Just
Oh, then the number is understood to be 1. So if you had like x plus 3 over x minus 2, that would be 1 over 1. So if it's just an x, thank you, Avery, if it's just an x, there's an understood coefficient of 1 in front of that. Okay? All right, so let's look at the problems now and go through them. Find the horizontal and vertical asymptotes and graph them. All right, so everybody remembers the rules for horizontals, so this should be easy. Take a look at problem number A there, letter A. Problem A. Tell me where the horizontal and vertical asymptotes are. Well, I have something at 2. What do I have at 2? That's my horizontal. So it's 2 over 1. So it's y equals 2. Look at the problem. Y equals 2. That's my horizontal asymptote. Now look at your denominator. Where's your vertical asymptote? X equals negative 3. Where do vertical asymptotes come from, kids? We just spent a couple of days talking about that. Vertical asymptotes come from whatever makes the denominator 0. Your denominator can't be 0. So you put a vertical asymptote there. All right, what about B? What do you want to do with this guy? Factor everything, okay. So when I factor it, I have x plus 2, x minus 2 over x plus 3, x minus 3. Right?
Yep.
Oh, nothing canceled. Oh, that's okay. That just means I don't have any holes. But do I still have asymptotes? Where are my verticals? There's 2 of them. One is at negative 3, x equals negative 3, and one is at x equals positive 3. Vertical asymptotes come from the denominator. Now look at your problem. Where's your horizontal asymptote? Look, your powers match, don't they? So what have we got? 1 over 1. So my horizontal asymptote is at y equals 1. Now slowly but surely, we're putting together these pictures. Eventually we're going to be graphing this. We keep adding pieces. Okay, next. What about this one? Okay, so the horizontal asymptote is 1 over 1. So y equals 1 is my horizontal. My vertical is where x equals 4. Now, if you've got a question about that, you need to stop me right now and ask it, kids. We've been talking about these. We need to get it sorted out. Asymptotes, where are they? 3 over 8, so y equals 3/8. So that would be like right here. Notice, when I write my asymptotes, do I ever put just the number? No, it's always an equation. Y equals or x equals. Every time you don't put a letter, you're going to lose a half point. So don't forget to put in x equals for the verticals, y equals for the horizontals. Where is my vertical this time? This one's a little harder. Can you figure it out? Negative 6/8, negative 3/4. And we know that because if we solve this, if we set that equal to 0 and solve, we get negative 6/8, which is negative 3/4. You have an asymptote wherever the denominator is 0. The denominator is 0 when x equals negative 3/4. Do E by yourselves right now, or with your partner, or with your neighbor. Do E. Yeah. Yes. Okay, so how are we coming with problem E? Did you factor your denominator? Alrighty. And when you factored it, you got x minus 2x plus 2, which immediately, hopefully immediately, told you were going to have a vertical asymptote at 2 and a vertical asymptote at negative 2. Because vertical asymptotes come from the denominator. Now this is our first kind of tricky horizontal one. Where did you put your horizontal asymptote? At 0. And why did you put it at 0? Because the power on the bottom is bigger. So your horizontal asymptote looks just like this. Right on top of the axis, y equals 0. Perfect. All right, next, do the next one. What'd you come up with? This is problem F. What'd you come up with for problem F? You had vertical at negative 4, x equals, and a vertical at positive 1. Very good, Jonathan. How about horizontal?
0.
Y equals 0. And again, that's because power on the bottom is bigger. Now take a look at this next one. Does it have any vertical asymptotes?
Vertical.
It has vertical at 2.
Vertical at 2, yep. There's a vertical at 2, perfect. What about horizontal? None. There is no horizontal asymptote. None. Because why? The power on top is bigger. There's no cap on it then. It just keeps getting bigger and bigger. And finally, this one, the top doesn't factor. I just made up some random thing up there. That doesn't factor. Don't worry about it. Does it have vertical asymptotes?
No.
Well, wait a minute. It does. It looks like it should have two, but it's the same one, so there's only one vertical asymptote. It's at x equals 2.
Yeah.
How about horizontal?
No.
None. Okay, you feel okay about that? You guys doing all right back there?
Yeah.
Okay, I don't even really want to know what's going on, but let's, okay. All right, 1.3. 1.3. It says BFF sheet. You don't have a BFF sheet because instead of giving you a sheet, I had you make the flashcards. I used to assign the flashcards for homework. Not doing that now. We did them in class. Okay, so don't worry about that. We do, however, need to open up our books to page 113.
Oh, good thing I'm look at my house.
And I need you to get out your flashcards, because we're gonna need our flashcards for these exercises.
What page is
We're going to 113, page 113. No, you're not gonna fall asleep, this is exciting.
I didn't say this period, I said next period.
Okay, well, that's all right, I don't care. You can sleep next period. We've got some exciting stuff to do.
Does it take out the flashcards?
Get out the flashcards, you need your flashcards. So, right now, Marissa?
Sorry,
Yeah,
Big reds.
Right now, we gotta have our book, hopefully each, there's some kind of book with you guys. We need a book, no book in the front row.
That's the next one.
Well, then turn around and join the people behind. Oh, you have a book, but where is it? Yeah.
I got a book. I'm on
He's
top
got
of
it.
it.
Look, this whole row has a book. This is lovely. You guys turn around and share with the people behind you. If you can focus, Marissa. You promise? Okay. Now here's what I want you to do. Everybody on page 113, and you got your note cards out. 113. We have our note cards out and we have our note sheets out. We have a lot of stuff.
Do we have
No. Now, I want you to look on page, I'm going to do the first couple for you, and then you're going to work together and do the rest, all right? But let's do the first couple because there's some vocabulary. I'm looking on page 113 at number 19. So I want you to have your note cards, and 4 of those note cards have functions that are called odd. Now let me tell you what odd means in case I haven't done that already. Odd means, I'll show you a perfect example. A perfect example of odd would be this function. Which one is that? That's a cubing function. Now here's why it's called odd. If you were a baseball player and you picked up this point right here and you threw it across the origin, so you threw it across the origin, it would land on another point on the curve. In other words, each one of these will match up with each one of these. That's what it means to be odd. It means you're symmetric about the origin. And you'll remember that, O, O. Okay? So let me give you an example of another one, and then we'll see if you can think of the last 2.
All right, well.
This is another one, the identity. Because don't all of these points match up perfectly with these? If I flipped them over? All right, looking at your note cards, there's supposed to be 4 of these. Looking at your note cards, can you find any others that have that match between quadrant 1 and quadrant 3?
Squaring.
Okay, now watch it now.
Identity.
Watch it. Let's look at the squaring function. Does the squaring function fit the criteria that quadrant 1 will flip over into quadrant 3? No. So that's not one.
Absolute never mind.
I got identity. Identity and cubing are the two I started with.
Reciprocal?
Oh, Avery says.
Oh, you
the
go,
reciprocal
girl.
function.
Avery.
Hey,
Yes.
that's my second.
Now listen. If you took these points and you flipped them across the origin, wouldn't you land on this set down here? Don't they match up?
Yep.
Okay. One more. Can you find it?
Greatest integer.
No. The dots aren't in the right spots. The open dots and closed dots. That's a tricky one. I hate that function. Which one? Sine. The sine
go,
function
girl.
is odd. Because if you took this hill and flipped it, it would become this valley. So the four functions that are odd are cube, identity, sine, and reciprocal. Don't you dare memorize that. You have too much crap to memorize already, right? We don't need to be memorizing that. What do we need to memorize? Odd means points in quadrant one are opposite, or origin, across the origin. They end up in the opposite quadrant. I love that. Odd means that points end up in the opposite quadrant. So you have a mirror image in the opposite quadrant. So whatever you had in quadrant one is mirrored in the opposite quadrant, 3. That's what odd means. Now, the next question says, name the six, oh wait, no, it doesn't say anything about even. Well, let me tell you what even means. Even means symmetric about the y-axis. So a minute ago, somebody said something about the squaring function. Do I have a mirror image on the other side of the y-axis? Yes. This is even. This is an even one. Can you think of any?
Absolute.
Oh, absolute value will absolutely be even.
Yes,
Got
sir.
tag.
What?
Can you think of any others? Look at your note cards.
Cosine.
Cosine absolutely is even. Mirror image on both sides.
Could we say reciprocal again?
Yes.
Now, no, we can't, and here's why. Here's why. If we folded this across the
Oh, it'd be
y-axis,
on top.
it'd be in the other quadrants, right? So it wouldn't be the same picture. Yeah.
I was thinking about that.
All right, next question. This is all vocabulary stuff. All right, the 6 functions that are increasing on their entire domain. Now, let me give you an example. We're talking about the 6 functions that are increasing on their entire domain. I'm going to go back to my cubing function. When I say it is increasing on its entire domain, I mean that when you draw the whole picture, your pencil is always moving up. That's what it means to be increasing. Can you think of any other, look at your note cards, there's supposed to be 6 of them. Can you think of the 6 that it's always increasing? Identity. Exponential. Okay, wait, slow down. I'm just chill out a minute. I can't go that fast. There's the exponential. There's the identity. Logistic. Always increasing.
Square.
What?
Square.
Squaring function.
Oh, wait. No, never mind. Square root. Square root.
The square root function.
Greatest integer?
That's a tricky one. We'll talk about it in a minute.
Yeah, you gotta go to the side.
I got the cubing here. It is. I got it. We have one more. The logarithmic function. Always increasing.
Yeah.
Now, before we talk about some of the other guesses and why they aren't right, these are the 6 that are increasing the whole time. When you draw these left to right, we always draw left to right, your pencil does nothing but go up. Now, somebody suggested greatest integer. when you draw greatest integer and you see these steps, it seems like it should be increasing because it's going up, 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 up. The problem is, your job was to find functions that every place your pencil's going up. When I draw this, is my pencil always going up? No, sometimes it's going sideways, right? That didn't count. Somebody else said the squaring function. What's wrong with that? Well, here my pencil is going down. So that's okay, it just isn't always going up, which is what the question was. Is that right? Okay. Next, the three functions, this is 21. The three functions that are decreasing from negative infinity to 0.
Wait, I'm so
What's the matter, sweetie?
Got the film going.
So 19 was the ones that are odd.
19 are the ones that are odd, yeah.
20 is the increasing.
Yep.
So then we have it wrote the increasing.
No, the increasing were those 6 right there. These were the 6 that were increasing. These were not.
I'm gonna just put my face in.
Okay? We cannot take a break until we get through a big chunk of this, so stay focused. Yes?
What was the squaring absolute value and cosine?
They were even. They were symmetric about the y-axis. There wasn't a question specifically addressing that, but we talked about odd, so we talked about even at the same time.
Calculate this.
Now, I'm looking at 22 or 21, and it says on the interval from negative infinity to 0, so right here, in this space, when you draw your picture, your pencil is going down. Now, can you think of curves that in this area, no matter what quadrant, any place over here, your pencil goes down as you draw it? Now, be careful. Cosine actually goes up and down, so it really can't be part of this conversation. It has parts that are decreasing, but it also has parts that are increasing. Cubing function does nothing but go up. We're looking for functions that go down on this side of the picture. The identity only goes up. Think about this, guys. That's the absolute value function. How's it going here? Down. That's what I want. I want ones that go down on the left side.
Oh, that's
Somebody said reciprocal.
cosine.
Yeah, that goes down on the left side.
The squaring.
The squaring function. Exactly. It's decreasing on the left side. Decreasing just means your pencil goes down. So when I draw these pictures, if I'm on the left side of the y-axis, my pencil is going down every time. That's what that one means. All right, now the next 3 I'm going to have you do by yourselves.
What's that bottom one called, Cameron?
But listen, I need to make sure you understand. Local extrema are tops of hills and bottoms of valleys. So apparently, there are 3 curves that have infinitely many high points and infinitely many low points. Number 23 says no zeros. What's another word for zeros? What are we talking about? We're talking about zeros.
Points on the
Uh-huh, very good. Points on the x-axis. So apparently there are some curves that don't cross the x-axis. And then the 3 functions with range, all real numbers, that means they go all the way down, all the way up, with no breaks. All right, so see if you can figure those 3 out. Work with each other, do it by yourself, I don't care. Use your note cards. You want 3 of each. You need 3 of each.
Well, I was just writing down what you said, numbers, but I didn't know what you were supposed to
Oh, no.
It touches it.
You ever felt the rush like this before?
I don't know. Figure it out with your partner.
Miss Ford, what does extrema mean?
Tops of hills, bottoms of valleys, high points and low points.
Extreme height and extreme
Highest
low.
points and lowest.
So you're saying like one that goes up and down?
What?
You like green
It never works. I do that every time, it never works. Precal, it's tough, really tough. Ever watch a student fail and then succeed? It takes guts, a lot of guts. Watch a class where students collapse, stagger, fall down, and cry. Yeah, Precal is tough, real tough. But go watch pain, swelling, and cry. Watch accomplishments ease the aches. Foes walk away as friends. Watch people become better people. Be true beauty, be honest people. This is Precal. Yeah, it's tough.
Oh my gosh. There
That's
it
a
is.
sin.
Come on.
For God so loved the world, He gave us Precal. 4:3:16. It's Catholic school.
We have that
Dude, it's not there. You have a girl. And you guys are on a break, man. Friends, the rainbow colored word is called
Kimmel's holding her head. All right, here we go. Let's see how far you got. Infinitely many extrema. Think about your sine and cosine, kids. Those are the easy ones. What are the sine and the cosine doing? Up and down, up and down. So what have you got? You got about 1 billion zillion tops of hills and bottoms of valleys, right? Infinitely many of them. The third one is tricky. In this interval, I hate this function, it's so tricky, but in this interval, it has that as a high point. In this interval, it has that as a high point here. So it has infinitely many high points depending on which piece of it you are looking at. Tricky. Those are the ones with infinitely many hills and valleys. Now, this morning somebody said, Mrs. Ford, the absolute value has a bottom of a valley, or, a bottom. And that's true, but it only has one, and the question said, which ones have infinitely many? So that doesn't count. Does that have a minimum? Absolutely. But not infinitely many of them, like these guys do. All right, then no zeros. This one was easier. You should have gotten this one. Which curves do not touch the x-axis? The exponential does not touch. The reciprocal does not touch. And the, what's this one? Logistic does not touch. Everybody else touches somewhere. Whether it's the origin or some other point, they all touch.
What's the name of the first one?
Somewhere. Exponential. Look at your note cards. That should be in your note card. Now, which ones have all real numbers for the range? Logarithm. Ooh, I didn't label my point. Sorry about that. Logarithm, cube, and identity. Now, again, this morning, someone suggested the reciprocal function, and their logic was perfect. She said, Mrs. Ford, it goes up forever and ever. It goes down forever and ever. How come its range isn't all real numbers then? Because it seems like it should be. It's broken in the middle, right? This piece is all below, this piece is all above. You don't have a zero. So it's not all real numbers, it's everything but zero. It never crosses the x-axis, yep. So these are the three right here. They have a range that's all real numbers. All right, we have one more vocabulary type thing to look at, and then we're going to draw some pictures. I may let you have a little breather break there. Maybe. Maybe. We got two more to go. So we've got lots of page. Number 25 and number 26. Now, 25 and 26. Use a notation. 25. Use a notation that you have got to be comfortable with. All right, so here we go. 25 and 26, please pay attention. This is real math, all right? This says find 4 functions. So in your pile of 12, find 4 that do not behave this way. Now, what does this mean? If you think about your graph, this says as x goes to infinity, which is here, right? As x goes to infinity, y, f of x is y, is also going to infinity. So in other words, as you go right, as you're drawing it and you go right, you also go up. So your job is to think of 4 functions that don't do that. Now, certainly the cubing function does do that. As I go to the right, I keep going up. Can you think of 4 functions that don't do that? They don't go up as you go to the right. That is beautiful, Jonathan. Now, it is going up as I go to the right. It's still going up, but it's not going to infinity. What's it heading toward? 1. It's like got a ceiling. So it's going up, but it's not shooting up into space. Beautiful. Can anybody think of another one? Somebody say cosine?
Yeah.
You're exactly right. What in the heck is the cosine doing? Who knows? It's going up and down, but it surely isn't shooting up into space, is it? Well, if the cosine isn't, then neither is the sine. There's one more. Now the square root, as I go right, I also go up. So that's not one of them. How about this one, guys? What happens as I go to the right? What's my pencil doing as I go to the right? It's not going up, it's going down. So these are the 4 right here that do not go right and up. Everything else goes right and up.
What's the one that's like the bottom left one?
This is the reciprocal function. Get your note cards out. Now, what does this one say? This one says, as we go left, we're also, y is going down. So can you name 3 pictures that as you go to the left, your pencil goes down? Cosine doesn't go down, it goes up and down.
Cubing.
Yeah, but I thought
Cubing. That one, as you go farther to the left, you go farther down. Identity. Farther to the left, farther down. Perfect.
So if cosine works for going up, why doesn't it work for going down?
It doesn't. Okay, this says they don't do that. They're not. These were nots. Okay, so it's not working for going up. It's not working for going down either. Greatest integer. Beautiful.
Oh my God.
Greatest integer. As we go to the left, our pencil keeps going down, down, down.
Logarithmic, do you want?
Oh, Jonathan, you are just on fire. The logarithmic function, guys, let's look at it. Jonathan says, how come the logarithmic function doesn't count? It's because, Jonathan, if we're going to approach negative infinity, we got to be over here. This is where negative infinity is. The logarithm doesn't even happen over there, so it's not part of that conversation. That is a great question, though. Okay? All right, now we're not leaving the room, but you can stand up, move around, stretch for a couple seconds, and then we're going to start graphing. No.
That's a good stretch.
Get up, stretch. If you have, do you really have to go? All right, hurry up. You'll be back here in 2 minutes. Hurry up, fill your water bottle, but hurry up.
All right, guys, it's break time. We'll get back to you.
Put it back in the bag.
What? That's my son.
Take that away.
And I go, go.
Listen, I have no
Go. Have your headphone out, put it away.
It's not out yet.
Don't get it out. That's what you need is one, hurry up, make it fast. What are you doing? All right, we're going to start sketching here shortly. Don't forget to sell your raffle tickets, folks, if you haven't done that yet. What are you guys doing?
A little cameo,
Probably. I can't even put it on there now.
Geechee, I got you. Geechee, I got you.
Okay.
That helps, Matt. That helps.
Right.
Any degree that helps.
We are going to sketch, kids.
I don't want to grab his pants because it's going to fly down.
It's not a strategy.
All right, we're going to sketch these, and I'm going to do this a little bit differently. I'm going to go ahead and sketch them, and then I want you to tell me what's going on. So A is the square root of x minus 5. That picture would look like this. This is the absolute value of x plus 1. That picture would look like this. Now, it appears that adding or subtracting numbers picks the picture up and puts it down somewhere else. Because a normal square root, the one on your note card, would have been seated at the origin, right? The normal absolute value would have been seated at the origin. But now they're not there anymore, they're moved. Now, interestingly enough, this one went 5 units sideways, And this one went 1 unit up. Did you notice that? Okay, so something's going on here. Can anybody surmise a guess here? Anybody want to suggest something? What seems to be going on?
It's like the B and Y supposed to be, right?
Yes. This is certainly like that. He said it's like when you have a line y equals 2x plus 7, the y-intercept, you know, picks you up 7. That's right. That's what's happening here. Mason, is your hand up?
No.
Okay, that's all right. Let me look at the next one and see if maybe we can catch on. That was B. All right, let's look at C. So C would look like this. And D would look like this. Okay, so what happened to C?
Just added one.
It just, well, it was like this one, right? It went up 1. What happened to D? It went left 1. Shoot, how do I know whether to go up, down, left, or right? What's the key here? The key here is where the number is. If the number is attached directly to the X, like this is attached to the X, right to the X. This, oh, I didn't write this down. This is attached right to the X. Then you move left or right. And notice that like everything else that's attached to an X, you go opposite. So this was X plus 1, so I came left 1. This was X minus 5, so I went positive 5. These two are not attached to the X. If they were attached, it would say X plus 1 like that. If they were attached, it would say E to the X plus 1 like that. They're not. They're just stuck on the end. And when numbers are just stuck on the end, it goes up and down. Now both of these went up. Why do you think they both went up? Because they are added. Let's look at E, problem E. First of all, what shape? The U, the parabola. What are you doing to that parabola? You're moving it because you've added or subtracted a number. Which way are you moving it? Up, down, left, or right?
Right.
It's going down. Kids, it would only go left or right if it looked like this. Then it would go left or right. If you attach the number with the X and then square it, or then raise it, or then absolute value it, then it moves left or right. If you just tack it on the end, then it goes up and down. So this would look like this. All right? Somewhere, I know I didn't leave you much room, maybe over to the side there. I want you to do a couple for me with your partner. Let's see how you do. Yep, right now you're going to do this for me. Let's have you do. Oh, tricky, tricky. Let's see if you can figure that out. Right here, this is a separate problem. You're kind of squeezing it in over here to the side.
Vayamos contigo.
Alright, here I got wild and wacky, didn't I? I put in 2 numbers. Alright, so start, what's the shape? Caroline, what's the shape of this? Look at its absolute value, so what's its shape gonna be? The V. It's gonna be a V. Now, the normal V looks like this, but we have moved it. See that 1 attached to the X? So it goes sideways, opposite of what it says. So if it says X minus 1, it's actually going to go forward 1. So it's going to go right 1. See that 5? Just tacked on the end? That's going to go up 5. So your V, it's the exact same V we had before, but now it's up here at the point 1, comma 5. It's the same thing we had before, just picked up, moved over.
Do you have to write the point that it's at too?
Yes. Marissa. Now, what about this one? Well, this is going to be some version of the square root, right? And it's got a +2. So here are your choices. Up 2, down 2, left 2, right 2. You know when you add or subtract, you're just moving it. So you just got to decide which way you're moving it. Look where the 2 is. Mason's back there going like this, and he is exactly right. It's going up 2. So we're going to have exactly the same picture that we had before. It's just moved up 2. All right, now we have 2 more things to do. One is we have to talk about another way to move these things. Have any of you wondered how you do this? What is that? That's an upside down square root?
Yeah, that's if we have a square root and it's like negative.
Exactly. No, not -2. Negative in front of it. This would be negative the square root. When you put, you guys, seriously? When you put a negative in front of your function, it turns it upside down. Okay? Now, what happens when you put a negative inside the function? Any ideas? Turns it that way. That's exactly right. So Vici, this would look like this. If you put the negative outside the problem, it turns it upside down. If you put the negative inside the problem, it turns it this way, sideways. So outside is upside down. Inside, talking about negatives now. Inside is this way.
Like a reflection.
Reflection. Across the y-axis. Okay? Now, everybody's going to get out a piece of paper. It can be a scrap piece of paper. Have negative and negative. So negative, that would do both things. So what I would do is I take care of this one first, flip it over here, and then turn it upside down so it can do that. All right, everybody got a sheet of paper out? It can be a scrap piece. It can be a half a piece. You don't even need a full sheet. I'm going to give you 3, actually 2. I'm going to give you 2 things to graph, and this is your exit ticket. Okay? So, That means that after you do these two and you show them to me, if they are correct, you leave. Okay? If they're not, you stay.
Let me get this. Let me get these problems out.
Alright, well, I hope you get them right. You need a piece of paper out. Each of you got any paper?
Yeah, I'm sharing the camera.
Okay, good. Good idea. So you're going to do two sketches for me. And you may use your note cards because you need to know your shapes here. So you may use your note cards. Okay, everybody got paper out and ready to go? Alright, so the first one we're going to sketch is y equals that. So make sure you copy it correctly. And that's the second one we're sketching. So those are the two that you're sketching. And then you will do them and bring them up to me. Excuse me, I'll turn this off. And I will